Okay, so let's quickly go through, once again, the necessary things you need to be able to do on the calculator on the AP exam for the calculator sections. So we'll quickly go through storage of a function, how to use derivative at a point, how to use the solver to find a solution on a specific interval, and then how we use definite interval. Those are basically the main things you need to be able to do on the calculator, in addition to graphing a function in an appropriate window. Okay, so we'll work off this question from 2014. We'll bounce back and forth between here and the calculator. So it says grass clippings are placed in a bin where they decompose on this interval 0 less than or equal to t less than or equal to 30. So we'll be using this window at some point. The amount of grass clippings remaining in the bin is modeled by A of t equals 6.687 times 0.931 to the t. So this is the amount of grass clippings. A of t is measured in pounds, that's an amount. T is measured in days. All right, part A says find the average rate of change of A on this interval 0 to 30, indicate units of measure. So let's jump to the calculator. The first thing I'm going to do is I'm going to store this function as A of t so I don't have to continue to type it throughout the problem. Okay, so I have 6.687 times the quantity, 0.931 to the t. Control var is the store feature, and we're going to call that A of t as it's defined in the problem. Our calculator doesn't do capital letters, even if you type them, so we'll just stick with lowercase. Okay, so from here on out, we can use A of whatever to refer to this function. Now, we're asked to find the average rate of change of A between 0 and 30. So I need my difference quotient set up. We're going to have the amount of clippings at 30 minus the amount of clippings at 0 over 30 minus 0, or just 30. Control equals to get the decimal approximation amount. So on average, the amount of clippings is changing at this rate between 0 and 30. The units here would be whatever the units are for A, which were pounds, and then whatever the units are for T, which is days. So this would be pounds per day, which means the amount of grass clippings is decreasing on average between 0 and 30, and that makes sense because they are decomposing. Part B says find the value of A prime of 15. Using correct units, interpret the meaning of the value in the context of this problem. Now, you are free to calculate the derivative of A by hand or on the calculator and then plug in the value 15. However, the calculators that we have a nice feature called derivative at a point, which I would encourage you to use. It cuts down on time and it cuts down on potential mistakes. So we want to use t as our variable. We want to find the value of the derivative at 15, and we want the first derivative. Our calculator sets up a template for us. It says d dt, the derivative with respect to t of some function, such that t equals 15. All we have to do is type in what function we want to differentiate. That's A of t. Hit control equals, and we have our answer really quick. So we have negative 0.163. Again, it's going to be pounds per day. Units for A divided by units for T. And this would be the instantaneous rate of change of grass decomposition at time equals 15 days. And then let's use part C here. Find the time T for which the amount of grass clippings in the bin is equal to the average amount of grass clippings in the bin over the interval 0 to 30. So we want the actual amount of grass clippings in the bin set equal to the average amount, not the average rate of change, the average amount of grass clippings in the bin between 0 and 30. So this is going to be an equation to solve. So here's our algebra menu. We're going to say solve. And before I type in the equation, let's come outside the parentheses. And let's go ahead and set up the restrictions on the domain here. So we want such that I only want answers that are between 0 and 30. I don't want all the solutions because there could be more than one or maybe two. It could be a whole bunch, and I don't want to have a bunch of calculator gibberish confusing me here. Okay, now what am I solving for here? I want the actual amount of clippings, that's A of t, and I want that set equal to the average amount of clippings. So the average value of the amount of grass clippings is that expression that has the integral in it divided by the length of my interval, 30 to 0. So my numerator is going to be Here's my definite integral, 0 to 30, a of t dt. Now, make note that the units make sense here. A of t is measured in pounds. dt is change in time. We've been measured in days. So I have pounds days in the numerator divided by days in the denominator. So the units for this right side are indeed pounds. So everything makes sense. All right, we're solving this equation for time. There we go. And remember, I want this stuff here on the outside, so I should close that parenthesis. And that's how my expression should look when I'm done. I'm solving this equation for t on this interval, such that 0 is less than equal to t, less than equal to 30. And let's see if our answers make sense. So in this case, we lucked out, looks like, and there was only one answer on this interval. I'm curious if I did not have the such that bar, if that would have mattered in this particular problem. There are problems where it does matter. Let's go ahead and check. Okay, so in this case, you were okay. But when trig functions are involved, especially, you want that such that command at your disposal so you can limit the solutions that the calculator displays. Okay, let's take a look at one more question. This is a tabular data question, and the prompt says the temperature of water in a tub at time t is modeled by a strictly increasing, twice differentiable function w, where w of t is measured in degrees Fahrenheit, so w is an amount, temperature, t is measured in minutes. At time t equals 0, the temperature of the water is 55 degrees Fahrenheit. The water is heated for 30 minutes, beginning at time t equals 0. Values of w of t are at selected times t for the first 20 minutes are given in the table above. So there's a bunch of questions before this part D, but here it says, for 20 less than or equal to t less than or equal to 25 minutes, the function w that models the temperature has first derivative given by w prime of t equals 0.4 square root t times the cosine of 0.06 t. So this is the derivative of w, so this is measured in degrees Fahrenheit per minute. It says, based on this model, what is the temperature of the water at time t equals 25? So we need to get the amount of degrees Fahrenheit, or the temperature at t equals 25. We have an interval 20 to 25, and we have this value of w of t at 20 minutes, 71 degrees Fahrenheit. Now, your mind probably goes automatically to, let's find an antiderivative, do the plus c, and solve for c. However, we have a calculator in our hands, and some functions we've seen do not have antiderivatives. Okay, so in this situation, we're probably not going to be able to do that. So what I want to direct your attention to is that we have this relationship again. We have w prime of t. There we go, w prime. We have the value of w of 20, and we're asked to find the value of w of 25. And there is a great calculus relationship that connects those three symbols. We need to start to become very, very comfortable with. And if you think about it for a few minutes, you'll probably come up that the relationship we need is the fundamental theorem, which says that the integral of a derivative is equal to the antiderivative evaluated at two limits of the integral here. Since we know w of 20, we can use our calculator to evaluate the definite integral of w prime, and we would define w of 25. All we have to do is add w of 20 to this integral. Notice that we're not using the calculator to find an antiderivative. We're using the calculator to find the definite integral, which is a number. All basic graphing calculators can do that. Only certain calculators can do antiderivatives. So if you're trying to do an antiderivative, you're probably not doing the right thing, because they're not going to give you an advantage because you have our model versus someone who doesn't have our model. Okay, heading back to the calculator. So let's again store this function w prime. So we have 0.4 times the square root of t times the cosine of 0.06 t. Store. Now you can store this as whatever you like. For me, I'm going to call it df. I'm going to call it dw, because that tells me derivative of w. I'm going to put of t. And now I want to set up my expression to find w of 25, which is going to be w of 20 plus that integral. From the table, w of 20 is 71 degrees Fahrenheit. So we're going to do 71 plus the integral from 20 to 25 dw of t dt. control equals 73.043 degrees Fahrenheit. That's a reasonable answer based on what's happening in this problem. So there you've seen the basic calculator features you will definitely need to use on those calculator sections, and I hope this was helpful for you.